Anyway, all right, thanks a lot. So I'd like to talk a bit about what it means to talk about a moduli space, a vacua. And so I think the usual way we think about moduli spaces of vacua, at least algebraically, and in this conference, is to think about them as algebraic varieties or schemes coming about from studying local operators inside of correlation functions. But what I'd like to propose is that a perhaps better way to think about moduli spaces of vacua is to think about them as stacks, rather than varieties or schemes. So to mathematicians, hopefully that doesn't come as too much of a surprise, because the theory of stacks has its origin in the study of moduli problems. And to physicists, you should be interested in this because, well, one reason to be interested is because if you forget about the stacking structure, then you're throwing out a lot of physics, actually, or can be, especially if you're interested in symmetries. So one of the things that the stack will capture that its underlying coarse moduli space does not is the full set of symmetries that your physical theory has, and not just those symmetries, but the 't Hooft anomalies that they have as well. So this extra structure, this stacky structure, can be really important for physics, for understanding the symmetries and the 't Hooft anomalies that you have in your problem. They're 't Hooft anomalies. So sometimes the symmetries aren't quite realized in quantum mechanics. They're realized perhaps projectively. So you may encounter projective representations rather than representations. And physicists call that an anomaly. So that's a very good reason to be interested in these type of moduli spaces. So I think these remarks are fairly broad, actually, and could be applied in a bunch of different settings. But I want to try to explain them and give some examples of what I mean by this in the context of this conference, which is theories with 8 supercharges and moduli spaces that are symplectic singularities. Okay, so I want to begin by giving some kind of cartoon introduction about what the picture is. So let me begin just by recalling one way that we think about moduli spaces in physics. Well, one thing we do is we start with something that you might call a chiral ring. So I'm going to call that A0, some algebra. And we get that by studying local operators, right? So the basic idea is we start studying correlation functions of local operators. And inside of correlation functions, it may happen you're in a situation, like in Tudor's talk, where inside of correlation functions, you can really just bring operators together in some meaningful sense and generate a ring or an algebra structure. So physicists often call this a chiral ring. And how do we build a moduli space from that? Well, one thing we can do is we can take a spec of that ring. So we can find a moduli space that I call M0, and taking a spec of that ring. And, you know, in the setting of this talk, this is something like an affine variety or scheme. And you can endow this with a lot more structure. So, you know, in the context of this conference, we're going to be putting a bit more structure here. For example, we might have positive grading on this ring, together with a Poisson bracket of a certain degree, and that would imply that with some properties, and that might imply that the moduli space here is a symplectic singularity. Question?
Can you remind me what a chiral ring is?
Chiral is just don't worry about the word chiral, it's just a word that people put there. It has some historical context, but It's an algebra that you form by looking at local operators. It's the algebra obeyed by local operators inside of correlation. It's just an algebra. You can,
Not necessarily connected to
yeah,
one takes that problem one.
I do want it to continue. Yeah, assuming I haven't specified dimensions here, but I'm going to be in dimension 3 or something like that. So.
At the moment, dimension isn't written on the board.
No, that's right. Yeah, if you like, I'm very happy to. Specify. So this could be viewed as a kind of operational way to think about a moduli space of vacuum. So instead of, if someone gives you a Lagrangian, some field theory, you might be able to compute the classical space of vacuum. This is a slightly different approach. It's more operational. It says, if someone just hands you a bunch of correlation functions and local operators and extended operators, doesn't matter where they come from, this is a way you can build a moduli space out of that. And so it doesn't depend in particular whether you have a Lagrangian description or not. It just says, if you have a bunch of local operators and correlation functions, this is one way you can build a moduli space of vacuum. Okay. So what I want to do, I want to generalize this slightly. So let me go right to here. So the thing that I'd like to do is extend this to include line defects. So again, this is very similar to Tudor's talk. So let me call this a line defect ring, alpha. And so the type of thing that we can imagine doing now is that we don't just study local operators, but we study local operators that are attached to line defects. So here's some line defect L, here's some line defect L prime. They might end on local operators O and O prime. And again, I can imagine situations where inside of correlation functions, just like in Tudor's talk, I can bring these situations together. Okay. And the type of ring that you get here is going to be have a grading. In particular, for example, I could pick a line. Maybe I should draw this now. I could pick some line defect and think about having powers of that line defect. And then I might call the ring of or the local operators that sit at the end of that line something like AN. And then I'm going to get to something like a graded ring. I'm going to have a grading. So alpha will be something like this.
And the line defects topological and they restrict to homology of the property picture?
Yes. Well, in this type of situation, when you have a graded ring like this, the natural construction is not spec, but proj. So that's what we're going to do. So from this data, you can build what you might call a moduli stack, or I will call a moduli stack. And the way we do that is by taking proj of this graded ring, or more precisely, a stacky proj construction. I'm not really going to say what that is. I'm just going to give you examples. So I don't really want to define this. But the type of situation, the type of space you're going to get is something like, in the setting of today, is something like a projective over affine variety or stack. And I'm always going to be in a situation where the stacky structure is very much under control. It will be like a Deligne-Mumford stack.
the definition of AN, you used one particular line.
I chose a line, so indeed, this is crucial for the story. So the moduli stack that I construct here will depend on the choice of line. That's crucial. You can think of it in specific examples. This would be something like a choice of stability parameter when you take a GIT quotient or Stacky GIT quotient. Think of it like that. Question? Yeah.
A0 appears in the line between. You also do the local.
Yeah, well, I'll come to exactly that point in just a second, but yes, you're quite right. This certainly includes what I did before, because if I take 0 here, that's the trivial line, and then I'm just dealing with local operators. I'll say more about that in a second, yeah.
Should we take on that as generating all the other conflicts, or is it a special choice of other conflicts?
Yeah, thanks for the question. Yeah, I'm being very schematic that you should. If you want to get a well-behaved thing, you're certainly going to have to put some conditions on what type of line defect you choose. Yeah. I don't think I want to say any more than that at this stage.
I have a feel for this. Is this generated by A0 and A1?
It's going to be in the examples I give today, but no, not in general.
Okay, right. So you probably wouldn't really need the stack if it was, right? Then it really is just a product over the base, which is the expected base here.
Right.
Yeah, so it's precisely when you have something more complicated.
Yeah, there are going to be situations like that. Otherwise, yeah, I believe. I might. Yeah. Okay, so let me address this point here about the inclusion. That this includes what we did before for local operators. Maybe I'll just draw this here. So as was mentioned, the structure here with line defects certainly includes local operators. But more than that, there's an action. Again, Tudor mentioned this in his talk in a slightly different way. Local operators can act on local operators at the end of a line. A special example of this. What does that mean? Well, it means that A is an A0 module. Right. Those local operators can act. And what does that mean on this side? Well, it means that I have a morphism, a map. Let's call it pi from M to M0. And in good situations, you can think about this as a resolution of singularities. In other cases, perhaps not, but call this a resolution in some generalized sense. Okay, so this is a bit formal, but you should view this as a kind of operational approach, where if someone just hands you a QFT, in terms of a bunch of operators, correlation functions, this is one way that you can build moduli spaces from that data. So this is one way that I like to think about moduli spaces. So what type of phenomena do you get? So why is this interesting? Let me again try to give a couple of cartoons. Well, one is the last thing I mentioned. It's a kind of resolution, or resolutions. And there are different types of things that can happen. So in the setting of this conference, the type of situation that I want to imagine is, let's write it like this. So here's this map. So the type of setting that I want to imagine is where my affine variety M0 is some symplectic singularity, some conical symplectic singularity like this. And there are different types of things that can happen. So, one thing that can happen is this map kind of resolves the singular point. This is something that I'm going to call a zero form resolution. I'll try to explain a bit more why, but the reason for physicists is because this resolution is associated to the existence of an ordinary zero form symmetry.
Would that be a one-form symmetry in four dimension? Or a
Yeah, it might be. Yeah, this is D is 3 is going to be important for this way of thinking, this classification.
Instead of having lines, you will have some operator.
Yeah.
Here then, four dimension of two conjugates here.
Yeah.
I can think of this as a final problem.
It's an algebraic way of introducing a finely Laplace parameter, right? But the reason why this is called zero form is because Fi parameters are associated to zero form symmetries. Yeah. That's right. Yeah.
No, sure.
So I'm doing the algebraic version.
Yeah, of course. I'm just asking about the 4D comment. I'm not sure whether it's one form.
It will be a one form, but my talk is in D.
No, sure.
So, yeah. So the other type of situation that can happen, which I want to talk about, is where the singularity is resolved in a different way. So the type of thing that I want to imagine is a setup like this, which is I'm going to call a one-form resolution. So I should say that for me, a resolved space means something which is a good target for a sigma model in physics. So this is a kind of very rough picture of a stack where it roughly looks the same as this singular space, but at the tip, there's some extra data here. This is the Stacky structure. And from a physical point of view, it captures the fact, this type of picture captures the fact that that at this tip, there's an unbroken ZM gauge theory. So for a physicist, this resolves the space in the sense that you can define a sigma model whose target space is this space. And this ZM gauge theory tells you how to deal with things at the tip. It tells you what's really happening there. So it makes sense as a sensible target. And this is this type of resolution is associated for physicists to what's called a one-form symmetry. So we will call it a one-form resolution.
It has nothing to do with the
It does, but I think explaining that is a task for later. Yeah. I'll give a bit more. I'll explain a bit more about what that means from a math perspective later.
Sorry to be annoying. And then
Question.
in 4D, will this one form resolution also be one form resolution?
Could we take 4D discussions to this afternoon? Because
that's completely fine.
it's more in the realm of things that I don't understand. So
Okay.
yeah. Yeah.
The zero form resolution that we create a massive deformation of the so in the one form resolution, you stay with the origin or you stay with the just
Sorry,
at the origin of the code there.
yeah.
So you start with something before the design of the code, you will execute the origin.
Yeah.
You're saying that here you got to use one form resolution, you will later escape the origin, just as you execute.
I think it's more like you'll have a free theory coupled to a Z-n gauge field, something like that. I'll give an example in a sec, so it's probably a better context to ask the question. Okay. So the other phenomena that you can have that's interesting is higher actions. So what does that mean? Well, let me again draw the picture here. So let's imagine I have some resolution that looks like this. Well, sorry, I need to draw this picture a bit down, so I'm going to start again. So another phenomenon that can happen is that you may find that you have an unbroken gauge symmetry at a generic point. So here, it just existed at the tip. But in general, you can have something, you may have an unbroken Z-n gauge theory at a generic point on the moduli space. That's also something that can happen. And then there's a connection to symmetries. So one thing we know is that zero form symmetries will typically act by isometries of your moduli space. It's the standard way, one way we think about symmetries. They can act by isometries. Well, one form symmetries are things that act by rotating this type of fiber here. Okay? So the message here is that in the ordinary sense, if you have zero form symmetries, ordinary symmetries, they act by isometries of your moduli space. If you want to understand higher form symmetries, one form symmetries, they act as automorphisms of the stack. If you throw out the stack, you cannot see those higher form symmetries. Yeah. You could, yeah. It's not, it ought to be, but it's not part of the package that I'm going to talk about today. I think then we're in the realm of algebraic stacks, which is a significant jump, if I understand. Yeah. The one form is spontaneously broken. Yeah, the consequence. This is Goldstone's theorem for one form symmetries. Okay. You have a discrete one form symmetry that's spontaneously broken. The consequence is that you have discrete gauge fields. That's what this fiber is capturing. Thank you.
I understand this one form resolution as an n-fold carrying. As an n-fold carrying over this n0 space.
Sorry, so that is
As an n-fold carrying.
N-fold cover.
no, I don't think you should not view it that way.
So, like, what's the alternate definition of one form resolution?
An alternative?
Yeah, like it's like a flat map with blah blah blah.
Yeah. I don't think I could give any definition yet. Just in the picture, but I'll try to give a concrete example in just a sec. So maybe that will help. Yeah.
To see if I understood the other question.
Yeah.
It's in so not this one, but this one.
Yeah.
Just BZN. So you can think of C form of CN.
Yeah.
It will give you this.
Yeah, that's my example
Exactly.
in just a sec. Yeah.
And then, like looking at, for example, sheet on this one.
Yeah.
It would be like the n equivalent sheet.
That's correct, yeah.
In your notation is using that it means the class plane space of the
Yeah. Well, the classifying stack. So in this talk, you could play this game in the homotopy world as well, but I'm going to be in the algebraic world today. It depends what what question you ask of your quantum field theory, whether you're going to be in, but. So these two ways that symmetries are involved are distinct. In one case, the symmetries are related to resolutions of the space, and in the other case, the symmetries are related to, they act on the space. And we sometimes call this A-type or B-type symmetries, or electric or magnetic symmetries, or Higgs branch or Coulomb branch symmetries. So this is the same dichotomy we have in 3D n equals to 4 theories.
So it's a similar one as the one in one.
No, it's the left and the right picture. So there are two distinct types of symmetries here. So one set are associated to kind of how you resolve the space. Another set are related to isometries or automorphisms of the space. And this is what physicists sometimes call a Higgs branch or a Coulomb branch symmetry. This is one way to view this dichotomy.
But this space maybe calculate this kind of set of yeah, just a kind of set.
It's just what?
Yeah, just a kind of set of points.
No, it's a groupoid. It's a category.
But you can maybe represent it in terms of some points.
Yeah, you could represent it in that way. Yeah.
What dictates whether we get a zero form resolution or a one form resolution?
The choice of theory. Let me give an example.
If the theory has a one form symmetry, is there always a one form resolution?
Yes. So just to summarize this, the idea is that this is one way to give a geometric perspective on the symmetries you have in your problem. There can also be mixed 't Hooft anomalies between these two. I'll mention a bit about those in a second. All right, so let me give an example. So just to try to, so it's the example that probably you're all expecting, and sometimes we've already talked about it a bit already here. So I might start with a symplectic singularity like this, C2 mod C2. And there are two ways that I want to talk about resolving this in my notion of resolution in physics. So in one case, it's going to be resolved in the standard way, in the category of varieties, to the cotangent model of P1. That's the standard thing. But I can also just, instead of viewing this as an algebraic variety, I can take a stack equation. Which is the thing that was already mentioned. So I want to talk about the physics realization of these two things. So the top one is very well known. Well, I think they're both fairly well known, but I want to go through them in a bit of detail, hopefully to provide a bit of a dictionary between physics and maths, so you can see hopefully things that are familiar in a setting that's simple. So let me deal with the case 1 first. So this is the standard one. It's very familiar. And the relevant theory is what we call super QED. So if I write it as a quiver, we normally write it like this, sometimes called U1 with 2 hypers, also called in Tudor's, just to make a connection to the previous talk, also called T of SU2. But it's this very simple quiver. So let me just go through kind of very concretely in my notation what happens. And I'm going to be talking about the Higgs branch of this theory. So let me first talk about A0. So A0 is the ring of local operators. Well, the way we compute that is we, again, borrowing from Tudor's notation, we have a bunch of fields. Sorry. Try again. We have 2 sets of fields, 2 x's, 2 y's. We're interested in invariance, and we need the equation by the complex moment map. Like this. So this is a very standard thing. I can write this in terms of 3 variables with this relation here, where say U is x1, y2, D is x2, y1, and W is say x1, y1. And then of course, in this case, if I compute spec of this ring, this is nothing other than C2 or T2 as a variety. So I feel slightly embarrassed writing these things down, but that's okay. I guess that's okay. All right, so let me then explain how to realize the nice resolution. So now we're going to look at line operators and local operators on which line defects end. So we have to choose a line defect, L. So we choose L to be the Wilson line of charge 1. Okay, same thing as in Tudor's talk earlier. What that means is that L to the n is the Wilson loop of charge n. And just a reminder, if I draw the picture, I'm now interested in local operators, an, that sits on which this Wilson line can end. Well, what type of local operators can Wilson lines end on? Well, they end on charged operators. So now not gauge invariant ones, but operators of charge n. So what are those? Well, if you squint a bit, pinch yourself that any operator of 0 charge can certainly sit here, provided I multiply it by something of charge n. And so this thing is going to be homogeneous polynomials in x1 and x2 of degree n. Notice here this depends on the choice of line, because I chose the Wilson line of charge 1. If I'd have chosen the Wilson line of charge -1, then I would have had y's here rather than x's. I could, yeah, and in this case it wouldn't really have made a difference. So I would have, spec comes with something, it would have changed it in a minor way. But if I shift the charges of these guys, that would make a big difference. We'll come to that, but in this setting, yeah. Okay, and in this case, if you compute proj of this thing, reproduce the resolution here. So that's how physically you see the resolution from an algebraic point of view. All right, let me say a few words about this.
So you define A only with respect to the specific line and not with respect to the item?
Yeah, I define it with respect to a specific line. In this setting, it's nothing other than the choice of stability parameter in the GIT quotient. Sorry? Yeah, because the x's have charge 1, the y's have charge -1. So, so let's talk about the two types of symmetries that we have. So we can ask first about isometries. So here's my silly picture of the resolved space. There's the P1 sitting at the end there. And there's an action on this space of SO3. This is the isometry group. Well, it's the isometry group that preserves the symplectic form. So the theory has an SO3 symmetry. Okay, marked well, I write SO3, I'm not SU2. On the other hand, if you look at these Wilson lines, WN, and this is going to be a physics statement, so I apologize, but WN sources a background. It's a Wilson line. So it sources a background for the U1 topological symmetry, or magnetic symmetry. So what does that mean for a physicist? Well, it means that if here's my Wilson line WM, if I look at a small disk here, D2, that it intersects transversely, then if I integrate over D2, the first Chern class of the background for the U1 topological symmetry, I'm going to get this integer n. So this is a physics statement. I'm not sure I can say this in a very good way. Okay, and then what do we have? Well, another property of these WNs is that you should think of the Wilson lines as basically line bundles on the target. Okay, that's a special example of what Tudor was talking about in the last talk. So how does that come about? Well, WN we will think about as the line bundle ON over T star of P1. Really, I mean ON and P1 pulled back. I'm just going to write it as ON. Well, this is completely tautological, but the reason why I say that is that this algebra here, this vector space AN, is then precisely sections of this line bundle, WN. Okay. So this is one concrete way you should think about line defects as being line bundles. The operators on which they end are sections of that line. Just the fact that they're charged. And so let me make one comment. So WN is SO3 equivariant. I'll explain what that means in a sec. Only if n is even. Okay, what does that mean? Well, if you look at this vector space here of homogeneous polynomials, This is a standard way to build representations of SU2. But not all of them lift to representations of SO3. Only those where it's even. Right? So for example, if n is 1, then that's a two-dimensional representation, which is not a representation of SO3. It's a projective representation of SO3. So there's some projectivity coming in. And that projectivity is related to an 't Hooft anomaly. So this fact that the Wilson lines can always be made equivariant with respect to SU2, but not necessarily SO3, this is a signal of an 't Hooft anomaly. Or this is what physicists call an 't Hooft anomaly. So for the physicists, let me write it down. Physicists like to write 't Hooft anomalies as invertible field theories in one dimension higher. So let me just write that down. So, see that I haven't left myself a frame. Let me write it somewhere. Down here. All right, so this is a mixed 't Hooft anomaly between the two symmetries I have in the problem. There are two symmetries, yes? One of those symmetries is SO3, that acts by isometries. The other symmetry was U1 topological, that's the resolution. And this fact about equivariant nature of line bundles is what physicists call a 't Hooft anomaly. It's a mixed 't Hooft anomaly between the two symmetries. Okay. W2 here is the second Stiefel-Whitney class, is the thing that obstructs lifting SO3 things to SU2 things. This C1 is the same, I introduced a different notation, sorry about that. It's the same thing that appears here. And you see the anomaly only cares about this number mod 2, right? So that's why mod 2 appears here.
Can I just say, so you define A and over the resolution of
Yeah.
Right. So suppose you exploit the resolution, like SU2 with obey. You can still define the Wilson line.
Yeah.
So what do you do then?
You would still do this construction. I think you would pick a Wilson line, you would complete proj, and probably you would find that proj is not going to give you anything new. I would guess. Define what?
Well, I mean, there's no resolution, no symplectic resolution. So how do you define the Wilson lines? Do you define the sections of a singular basis?
They're operators in a gauge theory.
Sure, but the question is the geometric definition. Because here you define it.
Okay, I see.
Yeah, it's gamma on the result X prime.
Yeah, okay. I mean, you're asking me, if I'm not really fully resolving the space, what does this mean? What does this interpretation mean? I think if I try to say anything precise, it's likely to be inaccurate.
But you're saying that the line bundles over the singular space are related to resolution?
Line bundles over the singular, no, the line bundles over the resolved space, right? There aren't many line bundles. That's the whole, there are lots of functions, but yeah. Yeah, the relation is this picture here. So notice this is crucial. So what I said was that a Wilson line introduces a background for the topological symmetry. Now the Fi parameter is in the same supermultiplet as the gauge field here. That's the connection. So you should view it as a discrete version. It's an algebraic way, a discrete way of turning on a real Fi parameter. But I don't know about real Fi parameters. I don't have a Lagrangian. Someone just hands me a bunch of local operators.
In this case of U1, we use the representations of the dividing filter and also the lambda, so we U1 as a dividing filter. So
Yeah.
Is it clear that
Good question.
So when we declare one by space,
Yeah, thanks, yeah. Indeed, so in general, there are going to be many more Wilson lines than labels that you would like to resolve the space, yes? And there's a map from one to the other, and the map goes by what background does the Wilson line induce? And it can happen that there are many different Wilson lines that induce the same class of backgrounds here. Okay. Yeah. I mean, again, this has a direct analog in kind of GIT quotients. So it's completely standard thing. Okay.
Well, I don't quite understand what is CT? Is it an integer or is it something you're integrating or you're integrating over what type of the people looking at what from? I don't know. Sorry.
This is supposed to represent a four-dimensional invertible TQFT. It's just a phase. Okay. So what's going on? Well, yeah, some four manifold, yeah. So this is the phase that an invertible TQFT would assign to the four manifold M4. And it depends on, it's a classical theory, it's invertible TQFT. It just depends on some background fields. So CT is the first Chern class of some line bundle that's associated to this symmetry. Okay.
How do you say CT mod working?
Okay, this is normally an integer valued class, and I guess I'm.
So, for the example of P1.
Sorry?
What is for the example of P1?
What is it for the example of P1?
I mean, what you're working at.
Still the example.
Yeah, I mean, you're talking about line bundles on P1, so then H2 of P1.
I don't think. This is a class on M4, some four manifold. Okay, so it's a bit different. I think if I try to explain this formula, I'm sorry. I think if I try to explain this in too much detail, it's going to take a while.
But the stability class is supposed to be abstraction to lifting the spin structure.
That's right. Yeah. So again, there's some background SO3 connection. There's some SO3 bundle on M4 because I have an SO3 symmetry here. And this is the second Stiefel-Whitney class, so it's the obstruction to lifting it.
Have a frame 3 bundle on M4.
An SO3 bundle on M4.
SO3 bundle on M4.
Yep.
It's the same as a rank 3 vector bundle with the
Yep.
form.
Yep.
I do want to lift it to a spin.
Yep. Yep.
What's the SO3 bundle?
I haven't told you about it. I just wrote this down because this is the way physicists like to think about anomalies. Okay.
So we should ignore it.
You can ignore it if you like. I can say more about it later, or I can write it in a more mathy way later. Yeah. But hopefully you see that it's related to projectivity. I think that's the crucial. Okay. Good. So I now want to talk about example 2 and kind of contrast it to this one. Again, these are very simple things, so feel slightly embarrassed talking about them, but
in particular, your quantity in your phase is always just going to be, that interval. I mean, it's always going to be 0 if you have this kind of stuff.
yeah. So let me now give example 2, just to contrast it, or at least write it in the same way, or the same type of way. So example 2 is what physicists would call, at least in one duality frame, a Z2 gauged hyper. So if you want to think about it as a quiver, you might draw it something like that. So let me explain what's going on. Well, if you have a free hyper, the moduli space is just C2, has an SU2 action on it, and the Z2 that I'm gauging sits inside here, it's the Cartan. If you want to be more precise, then in terms of these coordinates x and y, it takes them both to the negative. So let's again ask about the 2 cases. So if I deal first of all with genuine local operators, well, what are they? Well, if I just have a free hyper, I just take polynomials in x and y, and then if I'm gauging Z2, I just compute invariance. So that means that the moduli space, which is spec of A0, in this case is just C2 mod C2. Okay. What about the resolution? Well, again, to compute the resolution, I need to pick a line defect. And I'm again going to pick it to be a Wilson line, but it's now a kind of discrete Wilson line. So Wilson, it's a Z2 Wilson line. Okay. But now this has the property that when I square it, I get back to 1. So if I try and draw a picture now of what everything looks like, I've got A0 here, which is the thing that I wrote before. Then if I put the Wilson line, W, I'm going to have some vector space A1. But then if I go to the next step and I take W squared, that's just 1 again. So I get back to A0. And so on and so forth. So what's A1 in this case? Well, A1 can certainly have A0 stuff in it, but I can also multiply by x and y. Or I have to multiply by x and y. So you see, what are the things on which this Wilson line ends? Well, they're just things that are charged under the Z2. Right? So I'm just recovering the things that I lost when I took the quotient. But now they become operators attached to a Wilson line. And I'm not going to try to explain it in too much detail, but if you take what's called Stacky proj of this construction, this reproduces what we call the stack, C2 mod C2. So let me try to draw a picture of it. Well, the picture looks like this. As as a stack, the only stacky point is the origin here, which is where there's a dz2. Physically, this is just stating that at the origin here, when x and y is 0, there's an unbroken z2 symmetry. That's all. That's all it's really saying. There's also, again, an SO3 action. And I'm very clear that this is SO3, not SU2, because I quotiented by, I killed SU2, I quotiented SU2. That's what the picture looks like. And again, we can formulate much of what's going on in terms of this picture. So this time, some properties, so W, this now sources a background for a Z2 one-form symmetry. And again, I apologize, this is a physics statement. So whenever you gauge a discrete zero-form Z2, you're going to get a dual one-form Z2. That's what I mean. So again, the picture is like so. There's a small disk D2. Here's W. That's the property that if I integrate it over D2, the two-form background with a one-form symmetry, this is not going to be 0. And you can think about W similarly as a line bundle. On the stack. And this is basically all that, this is a bit tautological. This is all the Stacky project construction is doing. It's saying, invent a space on which I can think about the line as a line bundle. Okay. Sometimes it might be called a fractional line bundle on the course moduli space. But and the idea is that, again, like before, it has the property that sections of this line bundle are exactly this thing that I wrote down here. And again, a crucial point is that this is not SO3 equivariant. These sections here form it's X and Y, form a two-dimensional representation. So this is not a representation of SO3, but it is a projective representation of SO3 or a representation of SU2. So again, we have some projectivity coming in for exactly the same reason. And this gives you the structure of a 't Hooft anomaly. And again, in the physics, let me write down the physics way of expressing that. Oops, so it doesn't make any sense at all. We'll try again. So just to summarize the situation with symmetries, the stack allows you to see both the symmetries and the 't Hooft anomalies. There are symmetries coming from resolutions, symmetries coming from automorphisms. And the equivariance properties tell you about the 't Hooft anomaly. Okay, how am I doing for time?
10 minutes.
10 minutes, okay.
Maybe keep it started a bit late.
All right. Let me give one more example in the form of a picture. Question. Yeah.
Right, so the first example, like the theme of the workshop is like this symplectic resolution, right? Like so I'm happy.
Yeah.
So in the second one, the stacking stuff, so it's still have like symplectic something.
Yeah. It's a good question. I suspect the answer is yes. Actually, BZ2, I mean, I think the answer is yes, but I don't know how to define it properly.
Can you repeat the question?
I think the question is, this is a symplectic resolution. There's a symplectic form here. Is there one here? What does that mean? So, one very tiny observation is that if you take BZ2, or BZN, or something like that, has a two-shifted symplectic structure, which is the right degree that you would like. Find that. I don't really know how to make that precise. If you realize proj as a kind of, there's a way to think about proj as a GIT quotient. So do that, and then take the Stacky quotient instead.
What's the base case you start with? So it's okay.
Yeah.
I guess you could find something like symplectic resolution to be something that's symplectic and smooth, such that over the smooth local to the base, you know, it's an isomorphism that preserves symplectic stuff. In a sense, I guess that this is a smooth, this is a symplectic stack.
Yeah. That would be the hope, yeah. Although I'm going to give an example in a sec. We'll finish with an example where there's a BZ2 everywhere, more like a gerb. So let me finish with that example by drawing some pictures rather than doing the details. All right. So what I want to do now is another example. And sometimes called U1 with two hypers of charge 2. Another way to write it is as a quiver, where you put spin 2, like this. So let me try to summarize the situation. Well, you can kind of quickly convince yourself that the ordinary moduli, the ordinary Higgs branch of this theory as a variety, well, the charge doesn't really make any difference to that. This is an immediate reason why you should be suspicious of varieties as modular spaces. It just doesn't detect this charge. So, okay. What about M? Well, let me tell you what M is and then draw a picture. So in this case, you can think about M as a Z2 gerb over T star P1. And the gerb has a class, which is the non-trivial class, the H2 class here. So if you're not happy with gerbs, let me just draw a picture. So what does this thing look like? Well, here's the underlying T star of P1. And now there's an unbroken Z2 symmetry above every point on the underlying moduli space in the algebraic variety. there's again a zero form symmetry, SO3, that acts on the base. And there's a one form symmetry, BZ2, that acts on the fibers. So this resolution here is what we call the zero form resolution. And as it turns out, these two combine into what's called a two group. So you have a two group action. And it turns out that this is a non-trivial two group. What does that mean? Well, it has three pieces to it. There's an SO3 symmetry, there's a Z2 one form symmetry, and there's a non-trivial Posnikov class. So this is a non-trivial or non-split, rather, two group. And there's a nice way to think about what this thing is, this class here, theta. One way to think about it geometrically, it's the obstruction to an SO3 equivariant structure on the germ. So here we've got this kind of fiber over the base. There's an SO3 action on the base, and you'd like to make the germ equivariant with respect to that SO3. And you can't always do that. You can always make it SU2 equivariant, but not necessarily SO3. And the obstruction is precisely this class here. And so that's one way to think about the two-group structure geometrically. Okay. And again, as it turns out, there's a mixed anomaly between the two group that acts and the zero form that resolves for exactly the same reason as before, but I'm not going to write it down. It's even worse than I would have before. But again, all of the symmetries and all of the Tuft anomalies can be understood geometrically in this picture. What does the mirror look like? Well, the mirror looks something like the following. You take a kind of Z2 quotient of this theory. Really, you're quotienting a Z2 now in the inside of the action on the hypermultiplets. Let me not worry too much, but the moduli stack in this case is a kind of Stacky quotient of T star of P1 by Z2. So let me try to draw a picture. So here's one way to draw T star of P1. Here's the P1 base. These are the fibers at the north and the south pole. And the Z2 quotient basically kind of quotients like this. And so there are two fixed points of the action here and here. So there are going to be BZ2 fibers of these special points, the north and the south pole. There's a remaining U1 symmetry that still acts. It's kind of a quotient of the one you started with by Z2. And so this structure here is now quite interesting because we know from mirror symmetry that it's supposed to interchange the two types of symmetry. The symmetries that resolve and the symmetries that act get swapped. So whatever this mirror is, it ought to be something like a two-group resolution, whatever the heck that means. But you see, this is in some sense a combination. This is again a resolution of C2 mod Z2. In my sense of resolution. So you see, it's a combination of the two now. I'm resolving, I've got a P1 here, but I've also got some fibers. So this is what I might call a two-group resolution. And again, so you can see the symmetries, and you can also see the anomalies in this example in the same way.
So if you pick the line generic, then but I can also pick it like
Yeah.
generic and get this as 0,
Yeah, indeed. So underlying this is a choice of generic line. Yeah. I could have done either by specializing the choice of line.
Since it will 0 from 1 from 2 groups, is there a non-invertible resolution?
That's, well, I was going to finish on questions for this afternoon, and that's indeed one of the questions. So maybe do I have 2 minutes to
Sure.
give questions? All right, so 3 questions. One is a generalization of this example, which I might call symplectic duality for hypertoric stacks. So this goes back to, again, Tudor's talk this morning. There's a nice, well-known notion of mirror symmetry for abelian gauge theories, which is related to, which is a very nice example of what's called symplectic duality. But that usually places constraints on the charge matrix that Tudor wrote down, the unimodular. And this gives some hint about how to go beyond that. And it's very clear that if you want to go beyond that, you're going to need to look at Stacky stuff, I think. So that's one question.
Maybe just a comment, okay, maybe not the interpretation of in terms of Stacky stuff, but people in the 90s of mirror symmetry for any charge matrix that is modular or not.
In terms of Higgs and Coulomb branches?
Yes. I mean, in terms of gauge theories that charge matrices.
Okay, with charge half. What does charge half mean?
Afternoon, no?
Yeah, indeed, yeah. Yeah, indeed. So the second question is lift to a category of half BPS lines. So you notice that I drew the same pictures as Tudor earlier. I had line defects and local operators sitting at the end of them. You can interpret those as objects and HOMs in some category. What I've really been doing is Tanakian reconstruction. So someone hands you some nice category and trying to build a space out of it. I believe so, yes. And the symmetries can be seen in that, the symmetries ought to be able to see in that context as well. So there's now some category of BPS lines. It will fiber in some sense, or there'll be, that I'd like to ask Tudor about, over the space of resolutions or resolution parameters, including these higher form ones in general. And it will also carry actions. Two groups naturally act on categories. Right? Groups act on vector spaces, two groups act on categories. So this is the natural setting to study that. And then the final point 3. Well, in the last year, certainly the last year and a half, there's been a lot of activity on what are called non-invertible symmetries. So these higher form symmetries in two groups are fairly mild. They're still group-like, they're still invertible in some way. But we know now that lots of field theories, especially in 3 dimensions, have non-invertible symmetries. And you might ask how to incorporate that type of question into this setting. That was one reason for my wish to study Hilbert's series of disconnected gauge groups. One example is a pure gauge theory, whose gauge group G is given by something like PO for M. example, is if you take it to be a pin group. I suspect that incorporating these things is going to take us even further beyond the realm of stats to more categorical things. Everything is still invertible in the theory of stats. But one might nevertheless ask whether there's some geometric notion or otherwise that reduces to this, but also captures non-invertible symmetries. That's a wild question.
We have some symplectic singularities with several symplectic trees. I guess on each leaf there could be more about this fiber.
Yeah.
Do you expect any constraints on the type of fibers when I and if that's something you don't know? Typically we look at transverse slices.
Yeah.
You know,
I haven't thought about it in any substance. It's a good research question. So yeah, I don't have anything intelligent to say about it. So, yeah. I agree, it would be interesting to find.
So this is an example with the hypers of charge 2.
Yeah.
You talk about the zero form resolution and C2 measure. Is there a one form resolution in this case?
No, because the topological symmetry is just U1. There's no magnetic one form symmetry.
I have two questions.
Okay.
First question is rather classification. So the resolution depends on the choice of the line defect you chose.
Yeah.
So does that mean the global symmetries also depend on this choice of line defect?
But they might be realized in different ways.
Okay.
The choice of line.
And the second question is a quick question. So what happens if you also include could you expect something more exotic?
I think that doing so will be necessarily to properly understand. You're going to need to study lines attached to twisted sector lines to properly understand this setting. Well, you do. You certainly do. We wrote a paper about it a couple of months ago. Yeah.
Any more questions?
So, I mean, the C2 mod Z2 is very special.
Yeah.
Because you've got,
Yeah.
You've got a large group of sort of automorphisms. You've got a fundamental group on the smooth part.
Yeah.
Right, which is featuring quite importantly.
Yeah.
In your construction.
Yeah.
So I give you a symplectic singularity which has trivial fundamental group on the smooth part. And maybe it doesn't have very many isometries.
Yeah.
This has intermediate singularity.
Yeah. Yeah.
And you've got very few.
Yeah. Yeah.
So is there anything coming from this one form which you picked in that case?
No, I think you've captured the issue there, which is that all of the symmetries follow from the things you described. So if you don't have them there in the problem, then you're not going to be able to use them to produce resolutions, I think. Then correspondingly the field theories just won't have those symmetries, so you won't have the things available to you that you need to build these things. So I think there's a close correlation with the maths there. I'm not sure we're going to learn anything new in that sense from the physics picture.
Okay, then let's thank Mathew.